Guys? Hello? Okay.
Apa tu?
52, slide 52, chapter 2A, the one that I was up to you just now. Okay. So improving steady state error using PI controller. Okay. So PI controller is the second controller after P controller. Okay. Which is used to improve steady state error. Okay. Okay, so please remember, PI controller is used to improve steady state error, meaning that ESS from finite value to 0. Finite value ni 1, 0.5, 0.6, any value. So kita panggil dia as finite value. Okay. So we suppress the value, finite value, so that it becomes 0. This is done by placing an open loop at the origin and then increase the system type by 1. Okay. So kita introduce PI controller 0.1 over S. Usually this transfer function, or it also can be used as 0.5 over S, also can, or even smaller, S plus 0.01 over S. Okay, so because the zeros near the origin and the poles at the origin will cancel each other, meaning that we don't disturb the system order, okay, but we increase the system type. Okay, we increase the system type. So system type ada tiga jenis, type 0, type 1 and type 2. Okay, so for type 0, always relate to the KP, position error constant. Okay, and the error is E is equal to 1 over 1 plus KP. For type 1, okay, always refer to KV, position error constant, and the error is E is equal to 1 plus KV. And for type 2, we refer to KA. Okay, so the error is 1 over KA. So this is what I told you just now. Okay, so system type ni, kalau masih ada pelajar yang tak tahu, okay, dia adalah tengok pada open loop transfer function 30 S plus 1 S plus 2. Ini kita panggil type 0. Sebab dia punya ni S kosong. S kosong tu 1. Okay, so system type 0. Kalau dia bagi satu contoh 30 S plus 1 S plus 2, ini kita panggil dia sebagai type 1 sebab ini adalah S kuasa 1. Okay, seterusnya adalah G over S 30 S square S plus 1 S plus 2. So ini adalah type 2. Okay, because pembawa dia adalah S kuasa 2. Okay, jadi kalau dia type 0, always refer to KP. Okay, and untuk dapatkan KP is equal to limit S to 0 GS. And the steady state error is ESS 1 over 1 plus KP. So kena kira KP dulu. Baru masuk KP dalam ESS, baru dapat nilai. Yang kalau dia sistem type 1, kira KV dulu. Limit S to 0, SGS. Jadi ESS dia adalah 1/KV. Dan untuk type 2, kira KA dulu. KA is equal to limit S to 0, S square GS. Jadi errornya adalah 1/KA. Tolong ingat ni. Ini penting dalam design. Okay. Dalam frequency domain dan dalam time domain as well. Okay. So how to improve the steady state error? Using a PI controller. Ada dua cara. Satu adalah by using a gain controller or compensator. Okay. Jadi consider a system operating at a desirable response with closed loop at A. A adalah titik operating point dia. Kalau kita add 0 ke dalam sistem, type A is no longer a closed loop pole. Okay, so dia become another pole which is tidak melalui root locus. Okay, seperti ini. So to solve a 0 close to the pole at the origin has to be added. Okay, thus A is now a closed loop pole. Jadi kita introduce PI controller ini. K multiplied by S plus A over S. So that dia lalu dekat A. Okay, titik operating point tadi. Contoh. Given a system operating with a damping ratio 0.174. Ini adalah zeta. Okay, damping ratio. And then we add PI controller to reduce the steady state error to 0. Okay, for a unit step input 1 volt without affecting the transient response. So ini adalah dia punya plan dia. Okay, so kalau kita lihat plan dia, dia type apa ni? Sistem type dia apa? Shuffle.
0.
0. Sistem type 0 sebab dia adalah S kuasa kosong So dia punya strategi dia before controller design, before composition macam ni, and after composition macam ni. Maknanya ini adalah kita panggil dia sebagai PI controller. Dia fix S plus 0.1 over S. Okay. Ataupun S plus 0.01 over S. Ataupun S plus 0.5 over S. As long as dia punya 0 tu dekat dengan origin. Janganlah pilih S plus 100 over S. Tu salah. S plus 1000, S plus 10 over S tak boleh. Satu dan ke bawah 0.1, 0.2, 0.3 also okay. Jadi sistem ni ada type 1 macam si Sepul cakap. So kita kira lah dia punya KP dia. Okay. So KP dia adalah ini formula dia dan ini error dia. Jadi bila kita draw dia punya root locus, okay, -1, -2 and -10 adalah dia punya open loop poles. Ya. Okay. Kita lihat dia punya root locus ni adalah ada titik breakaway situ. Okay, breakaway point. Sebab breakaway point occurred between two poles, which is -2 and -1. Then one goes to the infinity, the other one goes to infinity, and this one goes to infinity as well. Okay, and the intersections between the root locus, the blue color, with the damping ratio 0.174 is here. Okay, and this is what we call as a dominant pole. Okay, dominant pole. and the gain is 164.6. Okay, 164.6. How do I get the value of 164.6? How do I get that? Macam mana saya dapat nilai itu? Adalah dengan menggunakan pengiraan, which is here. K is equal to berapa tadi? Minus 1, minus 2, minus 10. Okay. S plus 1, S plus 2, and S plus 10. Okay. So gantikan S sama dengan minus 0.694 plus J3 3.926. Okay. So gantikan ke dalam. Okay. So dapatlah nilai K. Faham tak? Tahu tak nak gantikan macam mana? Masuk je lah. Plus J 3.926 plus 1. Itu masukkan yang ni pula. Lepas tu masukkan yang ni pula. Okay? Boleh? Boleh tak? Cuba yang ni. Simplifykan yang ni. 1 tolak 0.694 berapa? 1 tolak 0.694. Osman?
0.306.
0.306. Real kan? Real. Kemudian imaginary dia 3.926. Itu. Kemudian yang ni, kemudian yang ni. Yang ini macam mana kamu nak simplifykan dia? Magnitude tu. 0.306 kuasa 2 plus J 3.926 square. Macam itu. Berapa? Kalau kita simplify ni. Awak kira, nanti awak kira yang pertama, yang kedua dan ketiga, same method, so akan dapat 164.6. Okay. Boleh? Boleh So the third pole is at minus 11.61. Okay. Which is second order approximations is valid. Okay, iaitu kita ambil nilai third pole tu minus 11.61 bahagi dengan 0.694 iaitu nilai real dominant pole. Sama dengan 16.73 which is greater than 5. So meaning that second order approximation is valid. Okay. Jadinya macam mana dapat minus 11.61 ni? Macam mana dapat nilai minus 11.61 iaitu third pole ni, iaitu daripada characteristic equations. Okay, characteristic equation ya. Jadi saya tunjukkan. Adalah K S plus 1, S plus 2, S plus 10, kan? Jadi dia punya closed loop dia adalah iaitu K S plus 1, S plus 2, S plus 10 plus K. Okay. And then the characteristic equation dia, okay, adalah S plus 1, S plus 2, S plus 10. plus K equal to 0. Jadi permudahkan yang ini. Okay, S square plus 3S plus 2 S plus 10 plus K equal to 0. Okay. Jadi kalau kita multiplykan lagi, so dia akan jadi apa? S cubic 3S square S cubic plus 10 S square S square 30S 3S square plus 30S 2S plus 20. S plus 20 plus K equal to 0. Okay. Simplify 13S square plus 32S plus 20 plus K. Okay. So insert lah K tu. Insert K tu. Sama dengan 164.6 tadi. Okay. Insert dalam. So dia akan jadi S cubic plus 13 S square plus 32S plus 20 plus K 100 84.6 equal to 0. Kira Q dia punya ni roots dia. Berapa? Kira bang. Koma ini tolong. S cubic 13 S square plus 32S plus 184.6. Berapa?
Salah ke?
Calculator.
Baru nak tekan.
Baru nak tukar.
Tekan.
Baru nak tekan. Tekan. Ada? Apa? Apa?
Saya tak tahu tekan. Lupa.
Astaga, mati macam ini. Farhan Fauzi. Awak kena tahu nanti test tak boleh buat. Farhan. Tak datang. Cyrus. Tak datang. Lukas. Okey, tengok pada ni.
Jumpa Doktor.
Berapa?
Negatif 11.61. Lepas tu negatif 0.693.
Plus minus G.
Lagi satu sama juga. Yang tu dia ada J.
J.
J negatif 3.92.
3.92. Okey. Betul lah. Betul ya. Okey lah. Betul ni ya. Nampak? 0.694 plus J 3.92 dan 11.61. Betul ya? Betul. Bagus. Okey. Faham tak ni? Ini cara kira third pole. Ni siapa ni? SX 190185 ni. Nama tak ada, saya nama attendant pun tak berti. Siapa ni? SX90185. Tak tahu nama siapa, attendant kosong ah. Siapa ni?
Hafizan Prof.
Tukar nama apa? Hafizan.
Sekejap saya tukar.
Macam mana dapat ni Hafizan? Macam mana dapat K164.6? Gain tu. Macam mana dapat tu? Negatif 0.694 J 3.926 3.926. Okey. So macam mana dapat K tu? Okey. Adakah saya dah tunjuk tadi? Saya dah tunjuk dah. Saya dah tunjuk. Satu kira formula, satu lagi pakai L1, L2, L3 kan? L1, L2, L3 iaitu dia punya jarak dia. Okay. -1, -2, -10. Ada dua cara. Satu guna formula. Yang ini K magnitude. Satu lagi pakai length. Okay. Jadi kalau dah tu, jadi kita balik pada slide. Okay. Dan KP-nya adalah 8.23 sama dengan ISS 1.08. So macam mana dapat ni? Di formula KP apa? Formula KP adalah, kita tengok balik, formula KP itu dia limit SGS S towards kosong. Okay. Di KP itu apa? Position, error, constant. Formula dia apa? Formula dia adalah limit S to 0 GS. GS tu apa? GS tu adalah open loop transfer function. Okay. Iaitu K sama dengan S plus 1, S plus 2, S plus 10. K itu berapa? K ini adalah 164 point. Berapa tadi? Satu enam empat 164.6. Okey. So gantilah. 164.6 ganti dalam ni 0, 0, 0. Jadi 1 darab 2 darab 10. Berapa? Benny, tolong. Benny Gumang. Tak datang. Cepol, tolong. 164.6.
8.23.
Tak dengar. Kuat sikit.
8.23.
8.2. 8.23 KP ya. Tu. 8.23. Steady state error ya. Berapa? Benny Gumang. Berapa? 1.8. Steady state error. Okay. Right. Jadinya gain for the third pole is the same with the gain of the dominant pole, which is 165. So this try and error, okay, from the gain of the dominant pole, maka kita boleh kira dia punya third order equations, which is this one yang tadi tu. Siapa kira tadi? Ha, ni. Okay. Right. Dan kita plot, so kita dapat dominant pole dan third pole. Okay. By computer, by MATLAB. Okay. So this is the program and the important information: gain, dominant pole, damping ratio, overshoot percentage, undamped natural frequency dan third pole. Okay. So kita lihat dia punya transient response dia before PI controller. Okay, which is this one. Okay, kita ada error. Okay, so ada error kat sini. Okay. ESS sama dengan 1 tolak final value 0.892. Okay, sama dengan 0.108. So this error must be eliminated. Okay, must be removed, must be eliminated. Okay, by adding a pole at the origin and 0 at minus 0.1, meaning that this sentence is S plus 0.1 over S. Itu makna ayat tu. Adding a pole at the origin and 0 at minus 1, minus 0.1. Okay. So with the same damping ratio, okay, this one, okay, so kita boleh compensate, okay, approximately as the same as before without disturb the transient, and the PI controller will increase the system type from 0 to 1, okay, and steady state error become 0, okay. Kalau kita redraw balik, okay, redraw, we still get the same shape of rule locus. Okay, 3 rule locus path ended at 3 infinity. Okay, as shown here. Okay, so this is the redraw. Okay, you can see that not much change on the transients. Okay, and after we simulate the PI and the plant together, okay, we obtain the response as shown here. After 35 seconds, the final value is 1. Okay, so the steady state error input is 1 volt minus final value 1 divided by 1, so it's 0. Okay, so it's fulfill our target. Okay, steady state error is 0, but after 35 seconds, setengah minit lah. So when we compare before and after PI, you can see that what is the observations here? The error here 0.892. The error here is 0. Okay, but after 35 seconds. So ini pun issue juga. Okay, because slow. Slow. Ini pun issue juga. Because error. Error exists. So dua-dua ada issue. Error exists sebelah kiri dan selepas PI error kosong, but nak achieve error kosong tu 35 seconds. So kita kena cepatkan dia. Cepat settlekan dia. Instead of 35 seconds, maybe 3.5 seconds. Okay. So when we compare the PI before PI and after PI, so this is the one that we see. Okay. So uncompensated tu is before PI. Yang ini adalah after PI. PI itu apa? Proportional integral controller. So in general transfer function, okay, PI controller can be represented by these formulations: Kp plus Ki over S, okay, or you factorize Kp multiplied by S plus Ki over Kp over S, or K sama dengan S plus Z over S. So Z adalah Ki over Kp. Okay, so this is the block diagram. The red dotted line represent the PI controller structure. Okay, and this is the model, the open loop transfer function. Both are connected, cascaded. Okay. So PI controller is designed by adding a pole at the origin and 0 at minus Z. Okay, S plus Z divided by S. The 0 is chosen to satisfy the transient response spec. The value of the 0 can be adjusted by varying Ki over Kp. Okay, so what happened is if the S equal to minus 0.1 or minus 0.01, also the error will turn from finite value to zeros. Okay, understand? On that, any question before I proceed? Any question? Ada soalan? Farhan? Sarul? Ada soalan?
Ada bro.
Boleh faham?
Boleh lah.
Bolehlah. Bolehlah tu macam kurang sikit lah. Syaiful, ada soalan? Syaiful? Okey, kalau tak ada soalan, kita bergerak kepada example 2.1. You are given an open loop transfer function which is K over S squared plus 2.5S plus 1. Design a PI controller to achieve a transient response as the following: overshoot percentage 10%, settling time 3.2 seconds, zero steady state error to unit step input 1 volt, verified design using MATLAB. Okay. So kita draw dulu dia punya MATLAB because dalam test and exams root locus are given. Okay. Oh. Kita onkan MATLAB. Nampak tak MATLAB tu? Nampak?
Nampak.
Amri?
Nampak.
Amri? Amri? Amri, macam mana nak plot? S sama dengan TF bracket S, okay. Amri bacakan G dia tu. K over one, K tu 1 lah over S square plus 2.5 multiplied by S plus 1. Right? And then R locus G. Okay. Then grid. Nampak? Nampak tak? Fahmi? Fahmi? Fahmi
Ya,
Asyik?
ya.
Komen sikit.
Sekejap saya tengah ada problem apa nak
Oh,
besarkan,
dengan drive. Oh ya.
nak besarkan skrin. Aduh.
Tak
Sekejap.
apa. Tak payah. Farhan.
Sekejap.
Farhan.
Ya, Doktor.
Komen sikit. Komen. Rule locus ada 2 path. Okay. Yang hijau dengan yang biru kan. Kemudian ni titik apa ni? Ni titik apa ni? Farhan. Breakaway.
Breakaway.
Breakaway berapa nilai dia? Minus 1.24. Okay. So kalau kita lihat sini. Sini. Rule locus start from poles. And then ended at infinity. Okay. And the breakaway point dia adalah minus 1.24. Okay. Right. So kita draw and then 10% ni adalah kita akan dapat nilai zeta. Dia ada formula number 1 kan. Formula overshoot boleh pakai. Formula zeta dengan graph. Standard. Okay. So mana-mana boleh nak pakai as long as dapat zeta 0.59. Kemudian zeta 0.59 ni cos theta sama dengan 0.59. Okay. Jadi theta sama dengan apa? Berapa ni sudut dia? Farhan. Sudut dia berapa?
tiga.
53 darjah. Okay. So theta sama dengan 53 darjah. Okay. Kemudian ambil protector. Letak kat sini. Kemudian bagi sudut dia 53 darjah. Dia cross kat sini. So bila dia cross kat sini itu adalah dominant pole. Okay. Dominant pole. Dia tak ada third pole sebab sistem ini adalah second order. Kan? Sistem ni second order. And sistem type dia adalah type 0. Okay, type 0. Tapi dia ada error sebab sistem dia adalah type 0, so kita kira KP dan gain dia kat situ adalah 3.5 okay over 2S plus 1, 0.5S plus 1, so KP 3.5. Error dia adalah 0.22. Okay, macam mana dapat KP 3.5? Sorry, macam mana dapat gain 3.5? Gain tu adalah K sama dengan tu dia, 2S plus 1 multiply 0.5S plus 1. Okay, gantikan S sama dengan minus 1.25 plus J 1.71 ke dalam. So, K sama dengan 3.5. Jangan tak tahu, mesti tahu ni. Okay. Then kita plotkan dia punya closed loop transfer function, TS. Okay. Which is G1 plus G. Bagi step signals dan kita dapati errornya adalah 1 tolak 0.778 berapa? 0.22. Okay. Ada error. Jadi kita kena hapuskan ini. Eliminate. Okay, using Pid Controller. Okay, so ni dah buat, ni dah buat, ni dah buat. So kita to achieve 0, kita add pole. Apa nilai nak letak? Ni nilainya. 0.01. Boleh. 0.1 over S boleh. 0.5 over S boleh. S plus 100 over S tak boleh. S plus 10 over S tak boleh. Mesti nombor yang kecil. Below 1. Okay. Dan biarkan KP sama dengan 1. So resketch balik. Find the closed loop transfer function. Dan kita akan dapat redraw dia macam ini. Tak banyak beza. Tetapi errornya telah kosong. Okay. Kalau kita lihat di sini. Error dia KP sama dengan limit. Masukkan nilai controller itu sekali. Okay. So infinity. 1 over infinity adalah kosong. Okay. So, kita tercapai nilai error tersebut. Dan ini adalah before Pid Controller ada error. Sambutan pantas. Tapi yang ini lepas after 600 second baru error 0, which is very slow lah. 600 second is about 10 minit. Kan? 600 bagi 60, 10 minit baru settle. Dah memang ngantuk, dah tidur dah. Baru error dia kosong. Jadi itu satu isu juga. Isu ada error, satu isu yang ini pula dah steady state error 0, tetapi transitionnya slow. 10 minit baru dapat steady state error 0. Jadi kita kena reducekan error minit ni, masa ni. Okay? Dengan menggunakan satu controller yang dipanggil sebagai PD controller. Okay, PD controller. So kita berehat sebentar. Okay, boleh guys? Berehat sebentar. Boleh?
Boleh, Prof.
10 minit rehat. Okay.
Boleh, Prof.
Sebelum kita masuk chapter 2B. Hai Cyrus, tadi panggil nama tak jawab pun.
Saya cuba-cuba tadi macam saya punya komputer ada error lah. Tidak dapat detect saya itu mic.
Nanti tak datang. Tak datang.
Datang.
Okay. Kita rehat sebentar.
Okay, thank you, Prof.
66.
66.42.
66.42. Okay, 66.42. So for all the compensated system, the closed loop poles have more negative real and larger imaginary part as compared to the uncompensated system. And it have a shorter settling time and shorter peak time. Okay. So it improve the transient response definitely. So we need to choose the proper value of 0 in order to do that. So I compare just now the graph. before this a table. So the table can be represented by the response. Okay, you can see that 0 at -2, 0 at -3, and 0 at -4. Okay, so I choose this one, the best one. Okay, if you choose this one also can, if you choose this one also can. Okay, because 0, -3 compromise between 0, -2 and -4. Example, given the system, design a PD controller to yield a 16% overshoot. Okay, 16% overshoot with 3-fold reductions in the settling time. So what do you mean by 3-fold reduction in the settling time? Let's say the pole, let's say settling time is 3 seconds. So the new one is 3-fold reduction, meaning 1/3 multiplied by 3. So 1 second, the expected new settling time. And 60% zeta is come from the 60% overshoot will give you the zeta value. Okay, so the zeta value come from this one. Okay, either formula number 1, overshoot percentage, or formula zeta, or the faster one is graph. Okay, 16%. Oh yeah. Okay, so the corresponding zeta value is 0.504. Okay, and the open loop transfer function is here. Okay, so is the third order system. System type is 1, kan? So KV, pakai KV lah. ESS dia 1/KV. And the open loop poles dia is 0, -4, and -6. Okay. So kita identify the 3 open loop poles, no zeros, system type 1. Determine zeta and theta from the given OS. So 0.504, theta dia berapa? Ini inverse cos 0.504.
Ya.
Allah Akbar.
59.74 degree.
59.7 degrees. Okay, catatkan. And then determine the intersection between the root locus and the zeta line and find the gain value. Gain value tu dia punya K lah. Find the third pole at this gain value. Third pole, jangan lupa to check whether the system is valid or non-valid for second order approximations. Dengan cari ratio dia. Ratio dia, nilai third pole dengan nilai real dominant pole. Okay. Calculate the steady state error 1/KV sebab sistem adalah type 1. Then identify the desired specification. Ini kita panggil sebagai steps. Okay, design steps ataupun dia punya SOP dia lah, standard of procedure, how to solve the problem. Boleh guys So ini diberi pada test dan pada exams. Okay, tak payah hafal lah So kita plot root locus. So ni tadi pemain ni berapa tadi? Theta ni 50
53.74.
53.74. So root locus ni diberi masa test, masa exam, print.
Sorry doktor. 59.
59. Sorry. Ni betul. Betul. Mana ni? Betul.
Betul yang tu betul.
Print pakai printer. Root locus yang diberi tu Kemudian dah print, ambil protector, letak dekat origin, ukur sudut 59, 60 lah, 60 darjah kan, senang. 60 darjah. Barulah dapat intersection dia dengan root locus. Dan ini adalah dia punya dominant pole. Bila dah dapat dominant pole, minus 1.2 plus 2.07, barulah kira dia punya K. Kan? Macam mana dapat K tu? 43.5. K tu adalah daripada S plus 4, S plus 6 kan? S multiply S plus 4 multiply S plus 6. Ini yang gantikan S sama dengan minus 1.2 plus J 2.07 ke dalam ni. Dan dapatlah nilai dia. K sama dengan 43.5. Okay. Macam mana dapat third pole? Macam mana dapat third pole? Okay. Third pole adalah, macam mana dapat third pole? Third pole adalah daripada characteristic equation. Apa characteristic equation dia? Iaitu S plus 4, S plus 6, S plus 4, S plus 6 plus K equal to 0. Jadi ini adalah S cubic plus 10 S square plus 24 S plus K sama dengan 0. So gantikan S sama dengan ke dalam, gantikan S pula. Gantikan K sama dengan tadi tu yang kita kira tu 43.5 ke dalam ni. Ke dalam ni. Okay, so dia akan jadi S cubic plus 10S square plus 24S plus 43.5 equal to 0. Okay. So kira roots dia. Kira roots dia, Lukas. Berapa roots dia? Lukas.
Negatif 7.59
Lagi satu.
dan negatif 1.20 plus J 2.07.
Okay. So ini adalah dominant pole. Dan ini adalah third pole, minus 7.59. Ni. Minus 7.6 tu. Oh, minus 7.59. Sebab itu dapat minus 7.59 atau 0.6 dekat situ. Faham eh? Faham eh? Tak faham nanti tengok YouTube balik. So kita simulate punya respon dia without PD controller 45.3 masuk dalam. Ambil close loop. Okay. Inject step. Okay. Boleh? Boleh eh? Tahu tak tahu cara nak program ni? Nak tunjuk? Nak tunjuk tak? Senyap je budak-budak ni orang tanya. Tanya macam dengan tanya kayu. Tengok sini. Okay, so kita type G kan. G tu open loop. G sama dengan 45.3 bahagi S multiply S plus 4 multiply S plus 6. Okay. Ini adalah open loop. Kalau nak cari close loop, T sama dengan G bahagi 1 plus G. Okay. Enter. So ini close loop. Jadi step tu kita inject dekat T lah. Step T. Gitu. Dekat close loop bukan dekat open loop. Then enter. Then letak grid. Saya share kan. Sama tak dengan apa yang daripada slide tu? Sama tak? Nampak? Ambil yang close loop. Jadi nak kira dia punya tu karakteristik, right click dekat mouse, pick response dengan settling time. Settling time. Keluar peak time je. 1.16. Okay. Settling time ni adalah 3.47. Okay. Sama macam graf tadi. Right. Okay, so kita draw the locus and then kita dapati bahawa overshoot 16% is equivalent to zeta 0.504. Close loop pulse dia yang ini. Okay, jadi settling time kita boleh kira by daripada time response ini, ataupun kita boleh pakai formula saja. TS is equal to 4 divided by real. Real tu maknanya real axis, which is zeta omega n, 4 bagi 1.205, 3.32 saat. Or TP pi divided by imaginary part, imaginary of the dominant pole, which is pi divided by 2.064, 1.52 seconds. And then KV adalah limit SGS, which is equal to SK divided by S plus 4, S plus 6, 43.35 divided by 24. And error itu adalah 1/kV, which is 0.55. Maknanya kV ni exist lagi lah. Okay, kV exist, 0.55. Right, so ini yang lama, before PD controller. Okay. So to improve to the PD controller, so kita kena lihat kepada sasaran kita, which is beside we having this settling time and peak time dan error ni. Okay, so kita perlu lihat pada apakah kita punya desired specification, iaitu settling time adalah 3/4 reduction of settling time. So 1/3 multiplied by 3.32, so this is the new settling time after we implement the controller, which is 1.107. Okay, so bila ini berlaku, maka dia punya dominant pole akan berubah. Okay, dominant pole akan berubah. Okay, iaitu TS new sama dengan 1.107, which is 1/3 daripada TS old. Okay, jadi sama dengan 4 divided by zeta omega n. Tetapi zeta tak berubah. Zeta tetap pada 0.504. Yang berubah adalah omega n. Jadi omega n sama dengan 4 bagi 0.504 multiplied by 1.107, which is the new settling time. So this is the new omega n. Okay, omega n new 7.17. So the real closed loop pulse now become zeta multiplied by omega n, which is minus 3.613. Okay, and the imaginary closed loop pulse J omega D sama dengan J omega n square root 1 minus zeta square, 6.193. So now the new closed loop pulse, after taking into account 3 full time reductions, is this one, minus 3.613 plus J 6.193. So this one is the new dominant pole, so we have to calculate okay, the gain over here and the zeros that we want to introduce to the system so that 3-4 reduction of settling time is achieved. So we draw a graph, a simple graph like this, where the open loop poles is 0, -4, and -6. And the new zeros from the PD controller, kita letaklah mana-mana dekat real axis. Nak letak sini boleh, nak letak sini boleh, nak letak sini boleh, nak letak sini boleh. Letaklah mana-mana. Just assumption sahaja. Okay. So dalam contoh ini, saya letakkannya di sini. Okay. Di sini. -Z kat sini. Okay. Dan kita kira sudut dia. Sudut theta 1, sudut theta 2, sudut theta 3 dan sudut theta 4. Okay. Jadinya sekarang ni saya kira, okay, so theta 1 adalah 180 darjah. Okay. Tolak theta, which is theta adalah inverse tangent 6.193 bagi 3.63, 59.7. So give you 120.26. Theta 2, ni dia. Theta 3, ni dia. Okay, guna inverse tangent. Kemudian gunakan formula angle criteria. Theta 1 plus theta 2 plus theta 3. Total angle from the open loop poles. Okay, which is this one is 0, this one is -6, and this one is -4. Okay, minus total of angle from the zeros, which is -z, unknown. This one unknown, theta 4. Theta 4 is unknown, equal to 180 degrees. So this one plus this one plus this one minus theta 4, which is unknown, equal to 180 degrees. So theta 4 is 95.6 degrees. Okay. So therefore, kita kirakan apa nama ni? Dia punya new zeros value itu using a graph, a simple triangle like this, okay, where this is -3.613, this is -z, this is the distance between -z and -3.613, and this is the alpha, okay, the angle under considerations. So tangent 84.4, okay, which is equal to 6.193, okay, divided by x, okay. So actually this one is alpha, okay. Alpha is 180 minus 95.6, which is 84.4 degrees. Kita masukkan kat sini, okay. So x sama dengan 6.193 divided by tangent 84.4, which is 0.607, the distance between these zeros and the real part. So kita tolakkannya, -3 plus 0.607, so kita dapatlah nilai z2, which is at -3. Okay, the PD value, the zeros value of the PD controller, which is this one. Okay, and the gain is 47.5. Okay, 47.5. Right, and then it will change the root locus to this shape. Okay, then the response is shown here by taking into account the PD controller. Okay. Which is S+3. So tengok ni dia turun. Settling time dia 1.15 second. Peak time dia 0.522 second. Okay. And it become faster. Okay, this one is before PD, compensated before PD, and this one is after PD. After PD control. Okay, so this is the structure of the PD controller. KD multiplied by S plus KP over KD, where KP divided by KD is equal to 3. Okay, then simplify. So kita dapat KP 47.5 and 142.35. So this is the final answer for the PD controller multiplied with the open loop transfer functions. When we compare before PD and after PD, so significant findings is there, 1.68 peak time. So the new one is 0.522. Settling time, the old one is 3.47 and the new settling time is 1.15 seconds. So achieved, okay? Achieved. The goal has been achieved. Any questions? Ada soalan?
Belum ada. Mau tengok balik.
Belum ada. Nanti revise balik lah. Nanti revise balik.
Betul.
Ya,
Kalau tak achieve, repeat balik step sama lagi false.
tak dengar. Benny tak dengar.
Kalau tak achieve, repeat balik step betul.
Repeat balik yang mana, Pak?
Macam contoh dia tidak menurun mendadak kan.
Tidak
Dia-
menurun mendadak.
Kalau dia punya peak time tu tidak menurunkan, kita buat satu lagi call lah. Satu lagi sistem. Juga betul.
Saya kurang faham soalannya. Kurang faham.
Contoh kan, kalau peak time tu tidak menurunkan, kita akan buat satu lagi PD kan, satu lagi.
Oh, tidak. Bila kau tengok sini, kan? Peak time yang lama 3.47, peak settling time, peak time yang lama 1.68. Jadi bila kita target 3-4 reduction settling time, so kita dapat 1.15. Jadi TP tu dia mengikut je, peak time tu dia mengikut je.
Oh, okay.
Dia ngikut. Kalau settle cepat, dia pun peak dia pun cepat juga. Sebab kita tak ubah dia punya zeta. Zeta tak ubah, 0.504 juga. Biasanya bila TS turun, TP automatik turun. Dia tidak akan kekal pada nilai 1.68. Okey, Benny. Cuba lihat contoh kedua. Contoh kedua boleh? Contoh kedua boleh? Tengok. Ni. Open loop transfer function 50 over S plus 5. Benny tolong komen. Ini transfer functions. Second order
Ini
second order system. System type. 0. System type 0. Okay. So dia suruh kira overshoot percentage dengan settling time. Dia tak ada bagi graph, dia tak bagi. Nampak? Biasa dibagi kan, sekarang dia suruh cari sendiri. Okay, so ini adalah open loop transfer function. Design a controller so that we have a 50% reduction in the operating system and 4-fold improvement of the settling time. Apa maksud? Katalah ini adalah 10% overshoot yang lama. Jadi yang baru sepatutnya 50% reduction tu maknanya 5% kan? 10% bagi 2, betul? Guys, betul?
Ya.
5% ya. Settling time 4-fold improvement. Tadi 3-fold reduction. Sekarang ayat dia 4-fold improvement. So maknanya katalah TS yang lama adalah berapa? 20 second. Okay, so TS baru fourfold improvement, maknanya 1/4 multiplied by 20, which is equal to 5 seconds. Okay. So open loop transfer functions. (50) S plus 5. Close loop berapa? Cyrus, close loop. Cyrus?
Ya, doktor.
Ini close loop. Okay. Then compare dengan standard second order equations. Kan? Betul tak? Omega n ni berapa? Square root 50. Cyrus?
7.07. 7.07.
Okay. 2 zeta omega n sama dengan 5. So zeta dia berapa? Cyrus?
.354.
Okay. Jadi dia suruh apa? Dia suruh determine the percentage ratus OS dengan settling time. Okay. Jadinya sekarang ni ratus overshoot sama dengan eksponen kan. Kosong 354. Kira kan? Berapa? Ni? Cyrus? Berapa? Yang lain pun kira. Berapa?
30.45.
30.45%. Okay, 30.45%, and settling time. Kosong 354. Mana omega n tadi? 7.07. Again, Cyrus, settling time.
1.598
Second.
second.
Okay. So, okay. So we already solved it. The part 1, and design a controller to have a 50% reduction in the OS. Okay. Jadi sekarang ni ni kan 30.45 kan. So the new OS will be 1/2 multiplied 30.45, which is berapa? Lukas? $15.23
15.225 lah.
23 lah, okey, boleh lah. Sesuai lah. Lebih kurang. Dengan cakap apa lagi spek design dia? And for full improvement of the settling time. Settling time yang baru, settling time yang lama. Yang lama berapa tadi? 1.598. Berapa? Lukas?
$0.3995.
Sesuai lah. 0.4 second lah. Boleh ya? Ini target. This one kita ke target. Okay. Spec destinations. Kita punya goal. Okay. Objective. Macam itulah. So, okay. So this one is the old one. Design yang mana ni dia, ni yang baru, new. So kita kena kira lah dia punya new close loophole. Kita dapat ni, tapi macam mana dapat? Kan? So kita kena buat macam ni. Jadi 0.4 second sama dengan 4 bagi zeta omega n new. So kita kena beri kira yang baru. Okay. Omega n new adalah 4 bagi 0.4 darab zeta. Zeta berapa, Mak? .354. Berapa? Omega n new? Cyrus? 4 bagi 0.4 darab 0.354.
28.25.
28.25. Okay. So, and then kita tahu bahawa new dominant pole adalah minus zeta omega n plus j omega d, which is minus zeta omega n plus j omega n square root 1 minus zeta square. Jadi kalau kita ambil zeta adalah still same, we don't change the zeta. Okay, zeta also been changed in this case. Okay, because kita dah turunkan ni 15.23. Okay, so 15.23 tu berapa? Dia punya zeta dia. Okay, dia akan berubah juga nilai zeta tu. Okay. .23. Jadi ini, sorry yang ini tadi kita kena buang dulu. Okay, sebab kita kena kira nilai zeta dulu. Okay, nilai zeta bila 15.23 kan. So ini buang dulu. Ini buang dulu So new zeta, okay, itu overshoot 15.23. Okay, ini new overshoot which is sama dengan eksponen minus pi zeta 1 minus zeta square. Okay, darab 100%. Jadi eksponen minus pi zeta 1 minus zeta square sama dengan 0.1523. Okay, jadi kita ambil ln di sebelah kiri dan di sebelah kanan. Ln 0.153. Berapa? Ln 1.053 ni, 153. Lukas. Berapa? Ln 0.153.
1.877.
Negatif, positif?
Negatif.
1.877.
877.
Jadi bila negatif, ni potong, ni potong. Betul? Betul? Betul bah?
Betul.
Jadi pi zeta 1 minus zeta square 1.877. Simplify kan ya. Dapat berapa? Zeta berapa? Tahu tak? Macam mana nak buat? Simplify. Okay, so caranya adalah macam inilah. Pi zeta 1.877 kan? Square root 1 minus zeta square. 1 minus zeta square sama dengan pi kuasa 2 zeta kuasa 2 1.877 kuasa 2. Betul? Cuba simplify kan? So akan dapat nilai dia lebih kurang nilainya adalah berapa nilainya? Okay, you simplify zeta tu dan kamu dapat omega n yang baru. So ini akan dapat the desired closed loop pulse. Minus 10 plus minus J 16.69. Okay. Dan gunakan angle property, so kita dapat zeros pada 25.29. So inilah dia punya PD controllernya 25.29. Okay. Dan cara pengiraannya. Jadi saya akan sharekan awak dalam WhatsApp. Okay. Solution example 5 ni. Nanti awak tengok macam mana saya selesaikan dia. Okay. Dapat tak? Dapat tak? Example 5 dapat tak? Konsepnya.
Dapat.
Jadinya kalau kita lihat di sini, okay. Okay, so the new one is 0.4 seconds, omega n 19.49. So kita multiply dapat minus 10, then omega d 16.73. Then the triangle will be like this to get the 25.32, the zeros value. Okay, gunakan triangle. Jadi nak kira gain either guna dua cara, satu guna length, satu lagi guna angle magnitude criteria. And this is the PD solutions. So buang S tu. Ni tak ada. Cuma 15 S plus 25 to 9 over S square plus 5S plus 50. And when we compare again, we reduce the settling time 4 times, okay? 0.835. Okay. As shown in the slides. Okay, kita berehat 10 minit. Boleh? Berehat 10 minit. Guys?
Boleh. Boleh, bro.
Oh, puasa the team. Stop share. Continue. Okay guys, boleh?
Boleh, Prof.
Sampai pukul 5 lah, boleh? Pukul 5
Boleh, Prof.
masak, boleh?
Boleh.
Harus sampai pukul 5 boleh? Tak ada Zarul. Kau main ni sampai pukul 5 okey tak? Alright, so kita terus kepada PID controller. Okay, so from the survey on industry based on impact and challenge by Tariq Samad in his IEEE Control System magazine, February 2017, telling that PID controller is a 100% impact rating. Okay, maknanya has been used a lot in industrial compared to other controller. This one is a MPC 78%, system ID 61%, process data 61%, and so on. Okay, this is why we have to look into the PID, proportional integral derivative controller. Okay, which is the function is to improve steady state error and transient response independently. Okay, so dia boleh improve steady state error and dia boleh improve transient response together under PID controller. Cuma kena buat independently, maknanya buat PD dulu, then after that PI, and then combine together. Okay, it's a combination of PI and PD controller. Okay. First, we have to design for transient response and then we design for steady state error. Maknanya PD dulu, then followed by PI. Okay. So the structure of PID controller is GPID, KP plus KI over S plus KDS. Okay. Kita boleh tulis dia macam ni. GPID equal to K S plus Z1 over S and S plus Z2. So the block diagram is shown here, PID controller, K1, K2, and K3. K1 is proportional, K2 is integral, and K3 is the derivative. So this PID is cascaded to the open loop transfer function GS, the model. Example 6. Given the system, so design a PID controller design so that the system can operate with a peak time that is 2/3 of the uncompensated system at 20% overshoot with 0 steady state error, input 1 volt. So maknanya peak time yang baru is 2/3 peak time yang lama. Kalau peak time yang lama adalah 3 second. Jadi 2/3 adalah 2/3 multiplied by 3 second, 2 second lah. The new one, the new peak time. Okay. Ni maksud ayat ni. And you are given 20% overshoot macam biasa, you will get zeta by the graph. I think the graph is 0.456. Okay, kalau guna formula 0.456. Okay, and then this one is open loopholes-nya adalah -3, -6, and -10, and open loop zeros adalah -8. So identify GS, which is 3 open loopholes, -3, -6, and -10, zeros and -8. System type 0. Okay, so kalau type 0, confirm pakai KP for the position error constant, and the error is 1/1 plus KP. Then calculate the zeta and theta from the given OS. Okay, so 0.456 theta-nya adalah berapa? Benny, inverse cos 0.456.
62.87.
Tak dengar.
62.87.
62.
Ya.
Point 87. Okay. So determine, dah dapat zeta, dah dapat degree, tulis gunakan protector, straight line from zero, from origin, and cut the root locus. So that is the intersection point, is known as dominant pole. Okay, and the gain as well. And the peak time at the closed loop time response is 0.298. So 2/3 is 0.2 seconds. And the new omega d is pi divided by omega d, which is 15.7 radian per second. So this is the plotting. This is your 0.456. This is the theta calculated by Benny. Okay, and then this is the dominant pole, which is negative 5.42 plus J 10.6. Okay, and the gain key is 1 to 1. Okay, so how to calculate gain K? I show you just now. Okay, either using length 1, length 2, length 3, or using the K formula. Okay, like this: K S plus 3, S plus 6, S plus 10, S plus 8. Okay, so you insert this value inside here, then you will get 1 to 1. Okay, value of the gain. And the time response of the closed loop is 0.702. Okay, for settling time. And for the peak time is 0.298, which is 0.3 second lah. Okay, 0.3 second. So that's why kita punya target adalah 2/3. So 0.2 second lah targetnya. So we draw the locus, and then the peak time is here, the old one. This is the dominant pole, the old one. Then how to get the angle 0, which is 18.37, okay, which is located at 55.92, the value of the PD zeros. Okay, so the PD zeros is shown here, okay, with the root locus connecting at 3 dominant pole. Okay, we choose this one, 15 plus 29.2 instead of the first one. Then we run the time response, so we obtain 0.2 seconds, which is fulfill the target. Okay. And for PI controller, so it's quite easy compared to PD controller. You just introduce S plus 0.5 over S. Okay, then multiply together with the PD, so you get the GPID, which is this one. Okay, and simplify and compare with the standard formula of the PID controller, so you get 4.6, 259.5, and 128.6. Okay. And the new one will get a 0.2 seconds with zero steady state error. So this is a new 0.2 seconds, and the error has been reduced, okay, after 7 seconds. So kita dapat steady state error dia 0. Tidak sampai 10 minit atau tidak sampai 60 saat, sekejap saja dah dapat steady state error 0. So when we compare, so we have a before design, which is uncompensated PD controller and PID controller, okay, which is a dark blue, which is give you faster transient response and 0 steady state error. So for this, I detail the solutions by giving you the solutions, the detailed solutions of example 6. Okay, I WhatsApp to you. Okay, dapat tak? Dapat tak? Dapat,
Dapat, Prof.
Okay. Right, so after PID, the problem with the PID is what number we have to insert into the controller, KP, KI, and KD. So we cannot simply key in any numbers without calculate first. As an engineer, you have to calculate using the knowledge that given just now and give the numbers, the correct numbers KP, KI, KD to the technicians so that they can key in into the controller. So for that, we need to tune the PID controller. Okay, tuning the PID controller, which is widely used in the industry for KP, KI, and KD. Okay, so it can adjust easily. Okay, but must be calculated first. Okay, so the tuning is involved the choosing the values of KP, KI, and KD. Methods depends whether you want to use online or offline. Okay, but we have some options. Okay, the following summarized table. First is manual tuning. Okay, this one usually otai or old timer. Okay, yang experienced persons can do the manual tuning, no math required. Okay, is the old school style. The second one is the Ziegler-Nichols method. This one is a proven method, online method, which is aggressive tuning. Or you can use a software tools. Consistent tuning can be online and can be offline, but it costs you money, some cost of the software and the training involved. So training also involve cost as well. Or Cohen-Kuhn method, which is only suitable for process control and first order system. So the best method is using a PID controller, which can give you the optimum value of the PID. Okay, because we are going to tune the KP, KI, and KD. So when you increase KP, KI will different, KD will different. When you increase KI, the remaining P and D will be different by looking at this table. Okay, for the rise time, settling time, overshoot, steady state error, and stability. That's why we cannot or difficult to obtain either in the form of differential equation or transfer functions. So we have to use Ziegler-Nichols method, which introduce effective method for the parameters adjustment by ultimate cycle method. Okay, So the ultimate cycle method have the procedure SOP as shown here. First is you set KD, KI equal to 0. The derivative and the integral set up to 0 to minimize the effect of the derivation and integrations. Then increase the KP gain until the system reach the critical stable or oscillate. Okay, so once the is oscillate, so we capture the critical gain and the frequency critical. Okay, Ku and omega u. Okay, in radian per second. Then calculate the Kp gain again. Okay, using the formula in the table. So the table must be included in the test and in the exams if you want to calculate the Kp, Ki, and Kd. Table of the Ziegler-Nichols. So based on the required type of controller, we can use this table. Okay, for Kp, for Ti and Td. Ti will go to Ki, Td will go to Kd. Okay, so this one, you need to have this value, 0.6 Ku, Tu over 2 and Tu over 8. Standard table for the alternate cycle method. And then you do this one, comparison with the standard Kp, Ki, and Kd. So you will get the value, okay, of the Kp, Ki, and Kd. Example, so design a PID controller for a unity feedback system, which is given by this. Okay, S over S squared plus 30S plus 100. Okay, so is the third order. Third order system, type 1. Okay, so we are required to tune this PID controller for the open loop transfer functions. Right, so we draw the rule locus plot. Okay, so this is the rule locus plot. Breakaway point. Ended at infinity, ended at infinity, ended at infinity. So the time response is shown here. Okay, 2.45 settling time, 1.11 peak time. So in order to tune it, so step 1, assume Ki and Kd equal to 0. Okay. Step 2, find the closed loop from the open loop. So this is the open loop. Find the closed loop, which is G1 plus G. Okay. And then the bottom closed loop transfer function, which is equal to 0, is the characteristic equation. Use this characteristic equation insert into the Ralph-Weiss table. Okay, so this is 1, 1, 30, 100, and 300 Kp. S cubic, X squared, S1, and S0. Then from here to here, continue the fill up. So in the theory, first column, which is this one, must greater than 0. So 10 minus 100 minus 10 Kp greater than 0. Simplify. So you will get Kp less than 10. 300 Kp greater than 0. Question 2. Kp is greater than 0. So when you consolidate 1 and 2 together, so the range of stability is 0 to 10. Okay, so if Kp is equal to 1, stable. But if Kp is equal to 11, unstable. But if Kp is equal to 10, so this one is critical. Okay, it's critical. Right, so Kp equal to 10, okay? So use this KP equal to 10, put inside the even equation. How do you get even equations? Even equations is we get from the Ruth-Lewis, which is this one. Okay. 30 S square plus 300 KP. Okay. 30 S square plus 300 and KP is the KU, which is 10. So this is 10. So insert inside. So 300 multiplied by 10, 3000. Okay. So 3000. So you simplify. Okay. S is equal to J omega. Okay. So you will get 30 J omega square minus 3000. So minus J omega is minus minus apa itu? Minus 100 kan? So minus 100. That's why dia punya omega U dia adalah J10. Okay, plus minus J10. And the frequency is 10, sorry. Frequency is 10. So omega 2 pi f equal to 10. 2 pi divided by TU is 10. So TU is 0.6283. Okay. So once you get the TU, so you can get the value of the KU. KU already there. KU is 10. And TU is the 0.6283. Okay. So you get the KP, you get the TI, and you get the TD. Okay. So KP is 6. TI is equal to TU divided by 2. So 0.3141. TD is TU divided by 8, 0.0785. But KI is KP divided by TI, 19.1. And KD is KP multiplied by TD, so 0.47. So we have the KP, KI, and KD value. And then we can give the value to the technician so that they can insert into the controller to achieve the PID controller purpose. The second example is also the same. Okay, it's a third order, type 1. The style of solution is almost the same. Okay, like the previous one, you just follow it. Okay, I think you can do it. Get the characteristic equations. Okay, and then solve for KP using the stability of the first column. Okay, so the omega U is square root 3 radian per second. And KP or KU is equal to 12. Okay. Omega U square root 3. So TU is 3.6276 because you are going to use TU inside the TI and TD. Okay. And KP as well. And then, so KP and KI is shown here. You got 4 and 3.26. Okay. So we stop here. Okay. Sarul, page 128, titik wakaf. Cyrus, can you jot down slide 128? Okay, guys. So we stop here our class to let our brothers, Muslim brothers, to prepare for the breakfast. Okay, meals for the at 7, 7:15. Okay, so kita jumpa balik pada 21 Mei lepas raya. Hello?
Okay, bro.
So test 2 until PD controller. through locus and sampai PD controller. Okay. I share to you past year test 1 just now, which have about 9 sets of past year test 1 questions, which will be discussed on the 21st of May. Okay, on the 21st of May. And then we have the test on the 22nd of May. Boleh? Boleh?
Test 1, 22nd May.
Test 1, 22nd May, petang, online. 21st May, discuss past year test 1 and lecture. Okay?
Okay, Prof.
Ada soalan? Ada soalan? Okay, I see you in 1 month time. Okay. During that time, I will release assignment questions. Okay. Thank you very much. Bye.
Okay, dah
Prof.
buka puasa.
Terima kasih, Prof. Assalamualaikum.